Hi, everyone. My name's Delaney Farrell. I am a PhD candidate in computational science in my fifth year. And at San Diego State, I study under Friedel and Weber. Today, I'm going to be talking about a project that we've been working on that models hot hypermassive neutron stars. So this project specifically focuses on modeling neutron stars in very unique conditions, namely when they're hot and hypermassive. Following an extreme astrophysical event like a binary system of neutron stars merging, a remnant neutron star can form that is much hotter than a quote unquote typical neutron star. With temperatures up to 50 or 100 MeV, this translates to like billions of degrees in Kelvin. These stars are likely to be rotating non-uniformly or differentially, meaning that the rotational frequency within the star is not constant. And this type of rotation supports very extremely high masses, well beyond the maximum mass of a uniformly rotating neutron star. Both the increase in temperature and differential rotation are characteristics that are kind of not seen in typical neutron stars. And due to these strange factors, these hot and hypermassive objects are only stable on short dynamical timescales, really only on the order of seconds, before they settle either into a more stable configuration or they collapse into a black hole. So this project as a whole kind of has two parts. The first is modeling hot neutron star matter, and the second models differential rotation in neutron stars. Modeling hot neutron star matter will not be talked about explicitly in this video or in the poster, but feel free to come and ask me about it during the actual event. So our focus will be on differential rotation. So with that, what does differential rotation actually do to a neutron star? So there's a few physical implications. The first I'll be talking about is an increase in mass. So if we imagine a non-rotating neutron star sitting somewhere out in space, it exists kind of as a balance between forces. So it's very massive, gravitational force pulls inward, and then it's balanced by a mixture of thermal and degeneracy pressures that push out. If the star is rotating, it adds this additional force, the centrifugal force, which helps to balance the gravitational force and adds more mass. For uniformly rotating stars, there's an upper limit on how fast a star can be rotating before it starts shedding or expelling mass from the equator. This is called the Kepler limit. And this also additionally sets the maximum mass a uniformly rotating star can be. But in the case of differential rotation, there can be frequencies within the star that actually surpass the Kepler limit, and therefore the mass of these stars can be greater than that of a uniformly rotating star. So other than an increase in mass, differential rotation also will deform the physical structure of the star. So I've shown kind of a diagram here on the left side that shows four panels. Panel A is spherically symmetric. This is what we assume non-rotating neutron stars look like. Panel B is what we assume kind of lightly differentially rotating or uniform rotating stars will start to form. So it's a kind of shrinking along the polar and extending along the equatorial axis. And then the bottom two panels, the quasi-toroidal and toroidal shapes, really are only seen in differential rotation, where the star is really starting to push out and might even form this rotating donut-like shape. So very strange physical implications for the star. I'll briefly touch on the numerical modeling for differential rotation. It begins by supplying something called the equation of state, which describes the pressure, density, and temperature relationship within the star. Again, if you're interested more in how temperature comes into play, please ask me on the actual date of the event. For modeling of differential rotation, the actual calculation begins with defining something that we call the line element in general relativity. It's comprised of these four metric functions that we solve for using Einstein's field equation, again in general relativity. This boils down to a system of 5 nonlinear partial differential equations that are solved in a self-consistent iterative fashion. once these are solved for, they're used to calculate bulk properties of the star, like its mass and radius. So using this numerical scheme, we're able to construct models of deformed neutron stars with varying degrees of differential rotation. So I'm showing here results for stars constructed at a temperature of 50 MeV. So in the plots here on the left side, the first column shows density profiles for two different stars. And then the plots on the right column are showing for the same stars the frequency distribution within the star. So the top row has a lesser degree of differential rotation characterized by this parameter A hat inverse set to 0.3. And the bottom row has a higher degree of differential rotation. So for the lesser degree of differential rotation, we see this deviation from spherical symmetry and ellipsoid-like shape starting to form. And then for the very high degree of differential rotation, we start to see this quasi-toroidal-like shape starting to form, the pinching at the top and bottom of the star. And then in the very bottom, I've shown some bulk properties about the star. I'll tune your interest to the last column in this table, T over W, or the ratio between rotational and gravitational energy within the star. We call this the stability parameter. And using some thresholds, we can determine if stars are stable or not against rotational instabilities. So this will all be talked about in the poster and more. If you're interested, please come and talk to me. Thank you.